For part 6, we were looking at circuits. And specifically, we have some of the equations stemming from Kirchhoff's laws and others. So we were dealing with the fact that voltage is given by the amount of current flowing through given resistors. The power involved in a circuit is the voltage times the current. And when you combine these two, that gives us power is IR, which is V times I, or I squared R. So these equations are true for all circuits. But if you have multiple resistors, we need to figure out what that resistance is. So with a series circuit, it's fairly straightforward. You have your electrical source, you have your 3 resistors, and the total resistance is the resistance of 1 plus resistor number 2 plus the resistance of resistor number 3. So when things are in series, it's very straightforward. But when things are in parallel, that's when they get very counterintuitive. So imagine now we have our source. And we have a circuit with 3 parallel branches. Resistance 1, 2, and 3. Well, we know that the voltage applied is going to be the current times the resistance. We also know that the voltage going through each of these has to be the same. Whatever voltage or potential you gain going through the battery has got to be drained when you come through the resistance and return to the battery. And here I've got the arrows pointed in the direction of electron flow and not current, because current was conventionally positive. But the energy that you gain going through the battery has to be counteracted by the energy that you lose from the resistors as you're going through. So this will actually have a very unusual effect in this case, because we know that the current is going to be split across these 3. So the total current is going to be the current through resistor 1 plus the current through resistor 2 plus the current through resistor 3. Well, going by our previous equation, the total current is going to be the voltage divided by the total resistance, because V equals IR, therefore I equals V over R. That means the current through number 1 is that voltage divided by resistor 1. The current through 2 is voltage over resistor 2, and the current through 3 is voltage over resistor 3. Now we notice we've got a common term of voltage in all of these. We can cancel it out by dividing both sides by V. And that gives us, for circuits in resistance, 1 over the total resistance is the sum of the reciprocals of the other resistances. So there's a very strange thing that happens here. This means the more resistors you add in parallel, the lower the total resistance of the circuit becomes. It's counterintuitive. You're adding resistors and producing less resistance. That's easier to see if we say that R1, R2, and R3 are all identical. So imagine that R1 equals R2 equals R3 is just sum R. Then 1 over R total is going to be 1 over R plus 1 over R plus 1 over R, which is 3 over R. And this means our total resistance is the resistance of each divided by 3. If you have n identical resistors, all in parallel, the total resistance is R divided by N. So every resistor you add reduces the resistance of the entire circuit. This is why houses have circuit breakers, because power outlets and other such things are all wired in parallel. You don't want to have to plug in the toaster and the microwave and a blow dryer and a hair dryer just to use the toaster. So we have them in parallel so we can use them independently. But that does mean if we plug in too many things at once, we draw too much current because that resistance is too low, and it is a potential fire hazard. Circuit breakers are designed specifically to prevent that. But this equation is where that comes from. This one right up here, saying that the total resistance in a parallel circuit is given by saying the reciprocal of the total resistance is the sum of the reciprocals of the other resistances. And if you have more than one resistor in a given branch, well, you treat those two like they're in series and the rest like they're in parallel.